In this lesson, we're going to take a look at determinants of matrices, and we're going to use determinants of matrices to help us solve systems of equations with Cramer's rule. It's a super interesting way to solve systems of equations. One of the higher level math courses that we offer, and that's part of a lot of different degrees, is actually linear algebra. In linear algebra, you learn how to do optimization using matrices, and you learn how to do different types of applications with matrices, including like things like finding traffic flow or determining probabilities of genetics. And so it's not just like math that uses this. It's not just mathematicians. We don't just sit in our offices and chart out these kinds of problems. When I took a graduate level linear algebra class at TWU, I had students in there from the kinesiology department because it was a requirement for their PhD program in kinesiology. And so sometimes these things come about in different ways that you might not expect. And so just kind of learning the basics of that information. So let's get started. The first part of this is determining or evaluating the determinant of a 2x2 matrix. So associated with every square matrix is a real number called the determinant of the matrix. So I'm going to pause for a moment right there and determine what it means when it's a square. A square matrix would be a 2x2 or a 3x3. The order of the matrix would need to be the same number of rows and the same number of columns, okay? And these would make what we call square matrices. You could go onwards and do 4x4s, 5x5s, and some very complex problems. You might have 100 by 100 matrices. But when they are talking about determinants, you have to be dealing with a square matrix, okay? Anytime a problem asks for you to find the determinant, it'll be written like this. The matrix name surrounded by vertical bars, 2 vertical bars, okay? So the determinant of any 2x2 matrix A is equal to AD minus BC, okay? So we would say that the determinant of A is equal to AD minus BC, okay? Let's do a couple of examples. Here we have the matrix 12, -2, 3, 4. It's in vertical bars, so we are finding the determinant. The determinant is going to be A times D, so 12 times 4 minus 3 times -2. So we get 48 minus -6, which is equal to 54. We're going to do the same thing on the second matrix. So the matrix we're asked to find the determinant of the matrix 3/8, 6, 1/3, 4. The determinant is going to be equal to 3/8 times 4, and I can rewrite 4 as 4 over 1. Okay, those two things are equivalent. Minus 1/3 times 6, or 6 over 1. When I multiply these fractions, I'm actually going to simplify first and then multiply. Both 8 and 4 are divisible by 4. 4 divided by 4 gives me 1. 8 divided by 4 gives me 2. So I end up having 3 times 1, which is 3, and 2 times 1, which is 2. Minus, I'm going to do the same thing over here. Both 6 and 3 are divisible by 3. 3 divided by 3 gives me 1. 6 divided by 3 gives me 2. So I have 1 times 2 over 1 times 1. So essentially I have 3/2 minus 2. 3/2 minus 2 gives me -1/2. If you're having a hard time thinking about that, you could think of it this way. 2 over 1 is the same thing as having 4 over 2. because if I multiply, and we're going to do this in a small cloud down here, if I multiply 2 over 1, both the numerator and the denominator by 2, 2 over 2 is just 1, so I've just done 2 over 1 times 1, which doesn't change the actual quantity or amount. It's still equivalent to 4 over 2. And so then I think about this when I'm subtracting fractions. I subtract the numerators and the denominator stays the same. So 3 minus 4 gives me -1, and the denominator stays the 2. So this is my determinant for this matrix. So now that we know how to find the determinant of a matrix, we're going to learn how to apply Cramer's rule. Okay, so Cramer's rule involves finding the ratio of several determinants derived from the coefficients of the equations in a system. So essentially, we're taking the information given to us in a system of equations, like this, and we're creating 3 matrices and finding the determinants of those matrices. The first matrix we're going to find is the matrix D. D is just going to be the coefficients of our x's and our y's, literally in the order that they are provided. So a1x plus b1y equals c1, and a2x plus b2y equals c2. And so our coefficients for x is a1 and then b1, we see those here, and then a2, b2, we see those here. So our first matrix is just created by the coefficients of our variables on x and y. Our dx matrix, okay, it's almost the same matrix, but we replace the x coefficients with c1 and c2. For our dy matrix, our x coefficients stay the same, and our y coefficients get replaced with c1 and c2. So if our determinant of D does not equal 0, then the system has a unique solution. The way we find that solution is we take the determinant of dx, divide it by the determinant of D, and then we take the determinant of dy and divide it by D, and that will give us our coordinates for our solution. It's kind of cool how this happens, and it actually might make solving these a lot easier for you if you like it this way. So let's solve this system of equations and let's see this in action. So we're told solve the system using Cramer's rule. Our D matrix is just those coefficients on our x and y values. So we would have 3, -5, 12, and 3. That's our D matrix. Our dx matrix, we replace our coefficients for our x's with our c1 and c2 are our solutions, but are on the right-hand side. So that's going to be 7 and 5, but the y coefficients stay the same. And our dy, the x coefficients stay the same, so 3 and 12, and our y coefficients get replaced with the right-hand side of the equation values, 7 and 5. And that's our dy. So what we need to do is find the determinant of each of these. So for this one, the determinant of D is going to be 3 times 3 minus 12 times -5. That gives us 9 minus -60, which equals 69. Our dx determinant is going to be equal to 7 times 3 minus 5 times -5, which equals 21 minus -25, which equals 46. And our dy determinant is going to equal 3 times 5 minus 12 times 7. I'm running out of space there, sorry. So that gives me 15 minus 84, which equals negative 69. Cramer rule tells us that our x coordinate is going to be equal to that determinant of dx, which we got as 46, divided by our determinant of d, which was 69. These are both divisible by 23, so this simplifies down to 2/3. And our y coordinate, let's do an orange, is equal to our dy that we found, which is negative 69, over our determinant of d. So determinant of dy over the determinant of d, which is negative 69 divided by 69, which equals negative 1. And so our solution to the system of equations is the coordinate pair 2/3, negative 1. So that's actually a little bit simpler to solve than if I were to try and use the addition method or the substitution method. So essentially what you've done is you've built up a tool, like a toolbox of different ways to address certain types of problems. And so we have now 3 separate ways that you could solve a system of equations, which is kind of awesome. You might be asking yourself, can I do this with a 3x3 or a system of equations with 3 variables? And you can. The only difference is you'd have to find out how to determine the determinant of a 3x3 matrix. And essentially what you do for that on a 3x3 matrix, let me make one up. Let's say 6, 2, 1, 0, 3, 7, 2, 1, 0. Okay, so what you essentially do is I always pick the top row. And what you do is you take the first value of the top row, so this would be a 6, and then you would multiply it by the determinant of the submatrix that gets created when you cross out the same row and column that you're in. Okay, so it'd be 6 times the determinant of 3, 7, 1, 0. Then when you switch to the middle row, you're going to subtract, and we take the number I just circled, 2, and you're going to multiply it by the determinant of the submatrix that remains, which is 0, 7, 2, 0, from here and here. And then we switched again, so then we're going to plus this value, 1, times the determinant of the matrix that remains, the submatrix that remains when I cross out its corresponding row and column. So that's going to be 0, 3, 2, 1. And then you would solve this. So in this case, it would be 6 times 3 times 0 minus 1 times 7 minus, or I can think of this as plus and like multiply out the negative 2, but I'll say minus 2 times 0 times 0 minus 2 times 7 plus 1 times 0 times 1 minus 2 times 3. And as long as I don't get a determinant of 0, I could use this to do Cramer's rule. So I'm like, you'd have to finish solving this. Keep going, just like solve what's inside the parentheses and then distribute or multiply it by 6, solve what's in these parentheses and then multiply it by negative 2, and then combine the terms at the end and finish and evaluate. But you can use this to solve systems of equations in 3 variables with Cramer's rule as well, because in that case you would have a1x plus B1Y plus C1Z equals D1. Then you would have A2X plus B2Y plus C2Z equals D2, and you would have A3X plus B3Y plus C3Z equals D3. And you could make a D matrix, which would just be all the A1, B1, C1, A2, B2, C2, A3, B3, C3 variables or coefficients. Then you could find your dx, where you replace the a's with your d's. Then you can find your dy, same thing. You replace your y's with your d's. And then you would find your dz by replacing your c coefficients for z with the d's. Okay, and so you see, these would be your matrices that you could create, and then you would find x, your solution for the x coordinate would be your dx, determinant of x, divided by your determinant of d. Your y solution would be your determinant of dy over your determinant of d. And z would be your determinant of dz over your determinant of d. And so you can actually use this for a 3x3 system. Now, I don't have a specific topic that asks you to do that, but if you really like finding determinants and think that that process is like easier than the multiple using elimination and then substitution process for a system of 3 equations, then go ahead and use it. Okay? If you have any questions about that, let me know. I look forward to hearing from you, and best of luck. Thank you.